Now today we are going to work on balancing the equations, and in this case we are going to focus on one of them, which is combustion reaction. Now up to this point I hope that you already learned about chemical reactions and you know that we have mainly four types of reactions: synthesis, single replacement, double replacement, and combustion. Now, whenever it comes to combustion, sometimes it becomes a little bit of hassle because we are dealing with big molecules. And unlike inorganic materials, that is main focus of our chemistry, in organic chemistry, the molecules can become real big. Now, sometimes the numbers are intimidating for some students, but if you follow the steps and orders that I'm going to explain and show you, you are going to have a fun time working with combustion reactions. Now,
Now let's take a look at combustion reactions. And when we talk about combustion reaction is nothing but hydrocarbons catching fire, basically mixing with oxygen. So in general, we symbolize hydrocarbons as CXHY, and these are carbons and hydrogens bound together with covalent bonds. And when they mix with oxygen, which results in burning, it is always going to give us two specific products. Now, products are always carbon dioxide and water, which actually puts us at ease because in compared to double replacement reaction, which might be a little bit crazy and you don't know exactly what you are going to get. In this case, if the combustion is complete, and again, this is a side note, the combustion is complete. That means there is enough oxygen in the environment for hydrocarbon to completely burn. So in that case, you are going to get carbon dioxide and water. Now again, if you don't have enough oxygen, you are going to get carbon monoxide, but this is not the case here. We assume that we have enough oxygen for the whole hydrocarbon to be consumed and burned. Now, to balance equations like this, we have to follow some rules, and this makes your life easier because I have noticed that sometimes students get intimidated by big molecules, C5H12 or even C10H22 and so on. And these big molecules sometimes result in big numbers as coefficients in front of each molecule. Now, in this case, if you follow the order that I'm going to explain to you, you will never be lost. Okay. Now be confident that you can do any type of hydrocarbon combustion reaction with ease. Now again, the starting point would be we are going to get carbon dioxide and water as a result. Now there is an order for balancing the combustion and it's spelled as CHO. Now remember this, CHO, CHO. Of course, C stands for carbon, H stands for hydrogen, and O stands for oxygen. Now, if you start with carbon, then hydrogen, then oxygen, it makes your life much easier and any kind of combustion reaction very easy to balance. Now, let's take a look here. We are going to balance the first atom, which is carbon. As you can see on the left side, you have only 5 carbons, C5, and on the right side of reaction, you have only 1 carbon. So yes, you guessed it right. The 5 is going to be a coefficient for CO2. So we are going to have 5 CO2s. Now the carbons are balanced on both sides. The second atom that we are going to look at would be hydrogen. We are going to take a look at the left side. We have 12 hydrogens, and on the right side, we have only 2 hydrogens. So to balance those, we are going to add a coefficient of 6 in front of H2O, which makes the number of hydrogens 12 on each side. And now we have balanced carbons and hydrogens on both sides. Now the only thing left, the last one, would be oxygen. As you can see, we have plenty of oxygen on the right side of the reaction and only 2 on the left. Now let's take a look. We have 5 times 2, 10 oxygens in CO2, and we have 6 oxygens in H2O. Add them together and you get 16 atoms of oxygen at the right side. Now, what number would make it 16 at the left side of the reaction? Yes, you guessed it right. Since we have 16 on the right, we need a coefficient of 8 in front of the oxygen O2 to make it 16 atoms of oxygen on the left side. Yeah, you have balanced your first combustion reaction, and as you see, just following the CHO it will make your life much easier. Now, let's take a look at something more challenging. In this case, C10H22O plus O2, and it's decane. Now we are going to again use the same rule that I explained, and let's just start with our products, which is nothing but carbon dioxide and water. Again, CHO, CHO, don't forget. Let's start with carbon. So we have 10 carbons on the left side. We are going to use that 10 as a coefficient for carbon dioxide. So yeah. Once we balanced number of carbons on both sides, the next thing that we are going to look at is CHO, hydrogen. So let's take a look. Here we have 22 hydrogens on the left side of the reaction, and we have only 2 hydrogens on the right side. So to make it balance on both sides, we are going to need 11 as a coefficient in front of our water. So yes, now we have balanced both hydrogen and carbon on both sides of this reaction. Now the last part of this would be, of course, oxygen. So in this case, we are dealing with big numbers, I know, and that's okay. No problem there. So again, let's take a look at oxygen on both sides of the reaction. Let's start with the right side. We have 10 times 2, 20 oxygen on carbon dioxide, and we have 11 oxygens on the water. If you add them together, you get number 31. So we have 31 atoms of oxygen on the right side of the reaction. Now at the left, we have only 2. Now that makes a dilemma because we are going to deal with something not whole number. Namely, if you are going to have a number as a coefficient that makes both sides the same, you are going to use 15 and a half, or nothing but 31 over 2. Yes, if you multiply oxygen molecule by 15 and a half or 31 over 2, then you have balanced the reaction. Well, theoretically or mathematically, you're correct, and that's fine. The problem is that we cannot have half a molecule. So to deal with this problem, we are going to multiply every molecule in this reaction on both sides by a factor of 2. So this factor of 2 is going to eliminate that half a molecule that we have and basically get rid of it. So if you just do that and you multiply everything at the left and right by factor of 2, then you are going to end up with 2 as a cofactor for C10H12, H22, 31 molecules of oxygen, 20 molecules of carbon dioxide, and 22 molecules of H2O, which of course, as you can see, these are big coefficient numbers, but that's fine, and there is no problem with that. And we actually are going to deal with big numbers whenever it comes to balancing hydrocarbon reactions. Now let's take a look at something else, and this is the last one that I'm going to show you, and then you can work on any problem that you want, and I'm confident that you can handle them. Now we are dealing with C6H12. Okay, in this case it's not an alkane anymore, it's alkene. Okay, it's a hexene, 6 carbons, and we are going to see how to balance it. Well, the good thing is, again, the reaction always provides carbon dioxide and water. So let's start with CHO, C, carbon first. 6 carbons at the left, then we are going to use a coefficient of 6 in front of the carbon. Now, once you do that, and yeah, I'm not going to show you the whole thing at once, but let's just imagine that you have a 6 in front of the carbon dioxide. Now, again, after you do that, let's go after hydrogen. And you have 12 hydrogen at the left, 2 at the right. So let's just use a coefficient of 6 in front of water. So we have 6 in front of CO2 and 6 in front of H2O. And now we have, if you can just imagine for a second, you have 12 atoms of oxygen on CO2 and 6 on water. 12 and 6 makes 18. So all you need to do is just add a coefficient of 9 to make 18 atoms of oxygen at the left. So this one was more of imagining it, but you can do it definitely much easier than I could have done it here. Again, you can solve any problem using the order of CHO. Don't forget CHO and you'll be fine. Okay.